Assalamualaikum and good day to everyone. My name is Adana Mesara binti Shamsul Hamran, and today I will be presenting our paper titled Design, Simulation and Interfacing of Add-on Circuit, or we like to call it STRATCH, which is SoC-Tracking Range Extender Attachment for e-scooters. Let me begin by outlining the key sections of the presentation: an introduction to the problem, literature review, methodology, results and discussion, and finally the conclusion and recommendations. E-scooters have become a popular mode of transport due to their eco-friendliness and cost efficiency. However, one critical limitation is their operating range, which depends on battery capacity. The project focuses on enhancing the e-scooter's range by integrating a dynamic throttle adjustment system that optimizes battery consumption based on the state of charge. The main challenge lies in the manual selection of throttle modes, which can lead to suboptimal battery usage. Users often find it inconvenient to manually adjust throttle settings to conserve power. This inefficiency results in limited operating range, which we aim to address with our solution. The primary objectives of this study are: first, to model and simulate the e-scooter's electrical and mechanical systems using Simulink Simscape electrical toolbox. Second is to analyze and optimize a dynamic current limiting algorithm to increase the e-scooter's operational range. And lastly, to design, test, and implement an add-on circuit to manage real-time energy consumption. This project focuses on both simulation and practical implementation aspects. So the scope includes developing a detailed simulation model of an e-scooter using Simulink, designing and testing an energy management algorithm within the simulation to optimize range, and lastly, building and interfacing add-on circuit with a real e-scooter for real-time testing for the system's ability to extend operational range. In the literature review, we've explored similar research that focuses on energy-efficient personal vehicles and torque allocation in electrical vehicles. Reviewed works related such as fuzzy PID control, where energy efficiency is improved by managing uncertainties in control systems. Next, distributed drive systems, where energy waste is reduced by optimizing torque distribution. And lastly, dynamic limiting algorithms, where control throttle to extend battery range. However, dynamic throttle adjustment based on SoC remains under export. So this project builds on these studies by proposing an algorithm for SoC-based throttle control. Here is the overall project methodology, which involves first developing the simulation model in Simulink to represent both the electrical and mechanical systems of the e-scooter. Then, design an energy management algorithm to simulate power optimization. The last step involves interfacing a Raspberry Pi Pico 2W based circuit with the actual e-scooter to perform real-world testing and refine the control system. Here are the operational flowcharts. So on the left side of the screen is the original e-scooter that relies on manual throttle selection. So when mode 1 is selected, the throttle input is limited by 60%. In mode 2, the throttle input is limited by 20%. The last mode imposes no limitation on throttle input, allowing the e-scooter to operate at full power. However, manual control leads to suboptimal battery use. While the automated system on the right side adjusts throttle based on battery level, SoC. So basically, if the SoC is above 50%, the system operates in normal mode where no throttle input limitation is applied. When the SoC drops below 50% but still remains above 20%, the system automatically switches to eco mode where the throttle input is limited by 20%. If the SoC falls below 20%, the e-scooter enters ultra eco mode where the throttle input limited is by 60%. So the result is smarter energy use, longer rides without any user intervention. Moving on to the simulation part of the project. We've developed two simulation models, which is first this one is without dynamic limiting for benchmarking, and this one with the dynamic limiter algorithm for comparison. But the main focus of the simulation is this figure, which details the throttle limiter algorithm. Here, SoC values trigger mode switches. So for example, when below 20% SoC, the system enforces a 20% throttle cap. This ensures energy efficiency without compromising usability. Lastly, for the methodology section, the selection of the microcontroller boards. It was selected based on compatibility and performance. Raspberry Pi Pico 2W was chosen for its 3.3 volts logic, GPIO flexibility, and UART support. Moreover, its low-cost, dual-core processor and MicroPython support, which makes it ideal for real-time throttle adjustments. Next would be the results and discussion section, where we'll be looking at the simulation results first. So the top left side graph compares how our dynamic limiter restricts the throttle input in different modes. So as you can see here, you can note how Ultra Eco in blue drastically reduces acceleration potential, while Eco in green balances the range and performance. The bottom side graph quantifies how throttle limiting conserves energy. In Ultra Eco mode, current draw is drastically reduced, while Eco mode offers a compromise and full throttle prioritize performance at the cost of higher energy consumption. Now, let's see how these throttle limits affect actual velocity. Here we can see the real-world impact of throttle limiting. Full throttle 100% achieves rapid acceleration, while 20% mode sacrifices speed for efficiency. This velocity profile directly translates to torque demands, as shown here on the bottom. The torque directly correlates with throttle input. The 20% mode in blue shows how limiting power reduces the motor strain and energy drop, while 100% in orange demands peak current. Analysis of the e-scooter's serial communication using a USB to UART board and real-time revealed that RX messages consist of 14-byte hex packets containing real-time data on speed, current consumption, and braking status. So key decoded bytes include brake light status and wheel position. The packets features a compact design for low latency updates with verifiable header, length, and checksum fields. Wheel position bytes were validated by manual rotation, confirming their role in trip or distance measurements. While the TX communication system transmits 22-byte hex packets from the user interface to motor controller, controlling the speed, throttle, and braking. Key decoded bytes include throttle positions, brake position, speed mode combining for mode codes, and front light status. Unlike RX wheel position data, throttle or brake hex values increment partially rather than fully, reflecting their control command nature rather than sensor measurements. Next, the schematic details the e-scooter enhancement circuit centered on a Raspberry Pi Pico 2W powered by a 43 volts to 3.3 volts DC to DC converter. Key features include a voltage divider for safe SoC measurement, reverse protection diode, multiplexer which is GPIO controlled, and UART lines for display communication. You can also see a purple switching wire which enables dynamic signal routing via the multiplexer to the motor controller, ensuring proper speed mode operation. Here is the breadboard prototype for an e-scooter range extending add-on circuit that features a Raspberry Pi Pico 2W as the main controller, a multiplexer for signal switching, and a voltage divider for 3.3 volts logic compatibility. The setup includes UART lines for display or motor controller communication, with GPIO pins managing multiplexer control. This testbed enables signal processing, voltage regulation, and switching validation before PCB implementation, allowing for easy debugging and modifications. Lastly, this is the PCB layout that was optimized for integration with existing scooter hardware. The design features optimized routing and well-distributed ground or power planes for stability. It dynamically controls speed, throttle, and SoC-based power modes with checksum validated real-time feedback for reliable operation. In conclusion, this project successfully demonstrated the feasibility of an add-on circuit for dynamic throttle adjustment. The simulation results validated the design's ability to optimize battery usage and extend the operational range of e-scooters. However, future work should focus on hardware integration with an actual e-scooters, real-world testing of the system under different conditions, and scaling the design for commercial applications. Thank you for listening, and it has been an honor to be given the chance. Thank you.